Okay, so first thing, A, calculate the spring constant, K, for the wire. So if we have a look at our graph, remember the spring constant is just the gradient where we are under the elastic limit. Okay, so if we go above the elastic limit, remember it no longer holds to Hooke's law, so we're only looking at the gradient below the elastic limit. So our gradient is going to be equal to our rise over our run. So if we have a look just up to the elastic limit, we've got a rise of 40 newtons over a run of 20 millimeters. 20 times 10 to the negative 3, which gives us a gradient and therefore a spring constant of 40 over 2,000, I get? Okay, now our units for our spring constant. Okay, we can work this out. Our force is in newtons, our distance is in meters, so it's got to be newtons per meter. The spring constant. All right. Next, calculate the strain potential energy that the wire can store before permanent deformation begins. All right, so again, this is the energy that our wire can store up to the elastic limit. If we go beyond the elastic limit, we get permanent deformation. So we want, if we're looking for our potential energy, we want the area under the graph. So our area, and here we've got a nice triangle, so we can just do a half times base times height. 1/2 times, so I'll use up to the elastic, well, we need to use up to the elastic limit. So our base is 20 times 10 to the negative 3. And our height is 40. So I get 0.4 joules. Okay, now calculate the work done to break the wire. We need the area under the graph again, but we can't just work it out with a triangle because it's not a nice straight line. So we would need to count the squares underneath it. So first of all, let's work out what each square is worth. So each square has a 10 Newton force on that side and an extension of 5 millimeters. So each square is going to have an area of 5 times 10 to the negative 2. And then there's a couple of ways you can do this. You don't have to count the squares that we used for the elastic limit, because we already know that there's 0.4 joules in that. So we can just count the other squares that are outside of that one. So if we get 3, I get 25. Anyone unhappy with 25 squares? Outside the elastic limit, I mean. Let's have a look at what this answer comes out to be. So 0.4 is the area under the graph to the elastic limit, plus I've got 25 squares above the elastic limit, multiplied by 5 times 10 to the negative 2. So I get 1.65 joules. So something like that. that's what the graph looks like. I can't go back a slide while I'm recording, unfortunately. So we worked out in part B, the area under this graph is 0.4 joules. So under this bit, that's where I calculated there's 25 squares, and each one is worth 5 times 10 to the negative 2 joules. And so we add those two sections together to get the total area under the graph.
Also, like the extension added, right?
Yeah. So it's the work done to break the wire is from the start. So it's from its point of 0 extension. How much work do you need to do to break it? Yeah, you're right. That should be a little more clear. Does that make sense? I know it's kind of funny doing it without seeing the graph. Okay. If you're okay with that, have a go at the next one, please. It's a similar type of problem.